Alright, welcome everybody to another edition of, not sure what to call this, but here we go. So basically, we're going to be doing chapter 17 and 19? 17 and, shoot. Anyways, air and air pollution as well as the climate change portion of it. For some reason, I decided to make this 108 slides. So what I'm going to do is some of these slides I'm just going to be like, have a look, and then I'm going to move on. And anything that I see that may need some explaining, I will do so. I will also put this video, or not this video, but the actual PowerPoint file in a Google Drive, and I'll share it publicly, and I'll put the link in the description. So if any of you want to look at that, you're welcome to. Alright, so air and air pollution. Let's get into it. So we're going to look at atmosphere as a resource. Atmosphere as a resource. Types of air pollution, the effects of air pollution, and then how some organizations and government type things are controlling air pollution. Here's some numbers you may want to keep in your head. The makeup of the atmosphere: 78.08% nitrogen, 20.95% oxygen, 0.93% argon, and 0.04% carbon dioxide. Ecosystem services, meaning what does it do for, life on Earth. Blocks UV radiation, that way we don't all immediately get cancer and die. It helps moderate the climate, and it redistributes water in the hydrologic cycle. So you've got all your clouds and stuff moving around up there, pushing water and moisture around the Earth. Types and sources of air pollution. So any chemical that's been added to the atmosphere by, it could be natural events or human activities, in a high enough concentration that is harmful. That's important. Some things are put into the atmosphere and it doesn't really have an effect on anything, but the pollution is high enough concentrations to be harmful. Two categories: primary and secondary. Primary is emitted directly into the atmosphere, and then you've got secondary, which is a substance that's formed in the atmosphere when a primary air pollutant reacts with substances in the air. And so a primary would be dust, right? And then a secondary would be like ozone or something, or a primary could be like methane. Secondary could be sulfuric acid, stuff like that. I think look at that. Okay, so here's a little chart for you to look at. Go ahead and pause it for a second if you want to take a look. Up next, I've got another little diagram that can show you where some sources of air pollutants can come from. Wildfires, vehicles, and other human sources. Looks like this guy's painting something with a spray painter thing. And then you've got like a volcano with just all that mess coming out of it. The classes of air pollutants: particulate material, also referred to as PM. Something that's measured, you might see it on like a weather report, is like PM 2.0 or something like that, and that's particulate matter that's larger than like 2 microns or something like that, and that can have a pretty significant effect on the air quality around you. And the higher that is, the more particulate matter is going to be in the air. Nitrogen oxides, sulfur, carbon oxides, hydrocarbons, and ozone. So particulate matter, all sorts of stuff gets in the air, whether it's soil and dust or soot or lead, or any of this stuff can get into the atmosphere from a number of different causes, whether it be the wind just picking up dirt off the ground, or it actually being released into the atmosphere. Two reasons it can be dangerous. you start breathing in all this stuff, it gets lodged in your lungs. You don't want that stuff in your lungs. It can also contain toxic or carcinogenic effects, which meaning it can cause cancer. Vocab word for you. Nitrogen and sulfur oxides, nitrogen oxides, and so these are some two things that you need to make sure you can distinguish between. Nitrogen oxides are produced by chemical interactions between nitrogen that's already in the atmosphere and then oxygen at high temperatures. Some problems with this are greenhouse gases, and it can cause difficulty breathing if it's in a high enough concentration. And a lot of times nitrogen oxides will be higher up in the atmosphere, so it won't really have too much of an effect on the human population, but once it gets to a high enough concentration and the right things with weather happen, it can kind of come down to our level in the atmosphere. Sulfur oxides, between sulfur and oxygen, and you can get acid precipitation, acid rain, whatever. It's not good for your car. You'll get hard water spots. Excuse me. Carbon oxides, carbon monoxide, carbon dioxide, oxide, and it's got carbon in it. Carbon, oxide. Pretty simple. These are greenhouse gases. Pretty straightforward. Hydrocarbons. So these are organic compounds, and hydro and carbon, hydrogen and carbon. Methane is a hydrocarbon. These are mostly what's related when you think of like a combination between particulate matter creating like a photochemical smog, meaning as the sunlight kind of comes down on this material, it will kind of become more dense and it will combine with greenhouse gases to become photochemical smog. And I've got 100 slides left to go here, so I'm gonna kind of start tapping through here. Ozone, I guess this is kind of important. Tropospheric ozone, so there's your levels of the atmosphere. The tropospheric zone is where people live and animals live and stuff. This is the lower atmosphere. It's a component of the photochemical smog. It's often created by some kind of interaction with something else in the atmosphere, not necessarily emitted directly. And then you got stratospheric ozone, which is above the troposphere. And ozone can actually be important in this area because it screens out UV radiation. But stuff like chlorofluorocarbons, CFCs, can make pockets in that ozone area or ozone layer, and can cause larger amounts of UV radiation to come through. Here's some sources of outdoor air pollution, transportation, industry, blah blah blah. Pause this if you want. Urban air pollution. Here's a picture of Los Angeles with photochemical smog. Sunlight, nitrogen oxide, and hydrocarbons come together, and that makes this. Here's a diagram on the formation of photochemical smog, your sources, what happens in the atmosphere, and then you've got your smog. Pause it if you want. Sources of smog. Here's a little pie chart that says where most of it comes from. Case in point. Here's an example. This is Beijing, and this is Mexico City. A lot of East Asian cities, being that they're extremely populated and tend to have a lot of industry around them. Tends to be a lot of pollution. That combined with the massive amount of people living in that small area, doesn't bring too good stuff. Effects of air pollution. You can zoom in on this or pause it, whatever, and look. It's a respiratory problem. That's basically what it is. It can also irritate your eyes. Health effects. Again, you can pause this and look. Children. This is kind of a big deal. Air pollution in children. Children who grow up in areas that have higher levels of particulate matter or ozone are much more likely to develop asthma. Asthma is becoming one of the larger problems in today's children because of these issues, especially the ones that live in urban areas. How the U.S. is controlling air pollution, something called Electrostatic precipitator. This may be something you might see on a FRQ, who knows. Basically, the smoke goes in, and you've got electrodes that can kind of pull off a lot of the pollutants, like not the pollutant, like I say pollutants, that's too general. Always pollutants is general word, try and be more specific. An FRQ. Particulate matter, stuff that can be pulled out of the air, so that it's just mainly smaller stuff, I guess you want to call it. It can go out into the air, but then you can kind of contain a lot of the particulate matter in a separate area and store that not in the air. This is that last picture, stuff coming out. This is the same building, I believe. It's just got this precipitator. This does not, as you can see, the massive difference. There's also air scrubbers, and there's a lot of different ways that this stuff is being treated. Like there's, whatever this thing, it basically sprays the smoke with water. You ever wonder how your gas gets to your gas station? A truck has to pump it in, and if you ever imagine filling up a water bottle, you ever turn a water bottle upside down in a big, like a pool or something like that, or a cup, and is dry on the inside? That's because the air has to escape before water can go in or liquid can go in. Same thing with a gas tank. You're pumping gas in, all that empty space with air with gas fumes has to come out, and so if you're just emitting those gas fumes into the environment, that's not a good deal. So trucks that pump this gas actually have systems that pump the air out and can recover a lot of that vapor and turn it back into gasoline and scrub it before it gets out into the environment. Clean Air Act, EPA can set specific air pollutant limits. Here's some things. Decreases in air pollution, apparently. Here's another case study. Ways to improve air quality. This, you can look at that if you want. Ozone depletion in the stratosphere. This is pretty important. Once again, ozone protects Earth from UV radiation. This is a picture, probably by NASA or something, and this is a hole. You see all this green stuff? That's where ozone is, and this is a hole in the stratosphere of ozone. And so you've got my computer's about to blow up here. I'm sorry, I'm kind of out of it at the moment. Oh, and this hole was identified over Antarctica. That's the southern pole. It looks like South America. Take a look at this. This is This is a example of skin cancer. Sorry, I'm not editing that out. Radiation. We all know how bad radiation is. Montreal Protocol, introduced in 1987. That's an important date to remember. Called for the reduction of CFCs, and it actually began using HCFC. I think it's hydrochlorofluorocarbons or something, which is a greenhouse gas. But it helps recovery of the ozone layer. Anyways, it looked to phase out a lot of the ozone destroying chemicals. Apparently it worked, or it is working. Acid deposition. These are some good vocab words for y'all to remember. Sulfur dioxide and nitrogen dioxide will react with each other, as well as water vapor. And will form acids, and basically it'll cause increasing levels of acidity. There's a picture of the pH scale. Here's a diagram of how acid deposition develops. You can take a look at that. The effects of acid deposition, aquatic animal populations, you have this acid getting into rain, and the rain eventually goes into water sources, and so on and so on. Bird reproduction actually comes to a decline because their eggs will become too thin and they'll start breaking. Calcium is an important factor in how thick the eggshells are, and that's unavailable in acidic soil. Here's how it can affect the forest decline, root damage, and stuff. Around the world, as I said earlier, you got Shenyang, China. Apparently, they only see sunlight a few weeks a year. That's awful. And this is more common in developing countries. Some of them even still use leaded gasoline, meaning they have actual lead in them. 5 worst cities in the world: Beijing, Mexico City, Shanghai, Tehran, and Calcutta, India. Almost said Indiana. Here's a diagram of how air pollutants can travel at high altitudes. So this is based off of the jet stream and stuff like that. There's not really much information on this diagram. So you think about the outdoors. Indoor is also important too. Pollutants can actually be 5 to 100 times greater indoors than the outdoors, because if you think about it, there's not much air movement or air cycling between the indoors and outdoors inside your home. Actually, efficiency standards work to make sure there's almost no transfer of air between the indoors and the outdoors. It's a cause for really efficient electricity and energy use, but not necessarily for the safety of the air inside your home. The most common pollutants: radon, cigarette smoke, carbon monoxide, all that mess. Radon actually comes from like radioactive rocks, uranium that can be in the ground under your house, basically, and that radon can seep through the foundation of your home and can get into your home, and as it builds up over time, it can begin to cause some serious health problems. Alright, so that's chapter, 17 or 16 or something. Chapter 18, climate change. This is a long one. We're on slide 39 out of 108. Almost there. We're about 18 and a half minutes in. Alright, our core case study. Ice cores, if you've ever seen them, they drill into the ice and they take out a big core, and you can kind of tell the history of the climate and all sorts of mess about the world based off of like the layers of ice that have frozen over the years. Let's see, ice in Greenland actually holds 10% of the entire world's fresh water, and it's the largest island, but 80% of it is covered by glaciers. This next picture, this is what it looked like in 1982. All the white is glacier, all the red is not. Look how much this is beginning to expand. Like the total area of this ice that melted from here to here is what is this? Total area of Greenland's glacial ice that melted on July 8th, 2012, which is the red area here, is significantly greater than the amount that melted during the summer of 1982. So this is just during the summer. Summer of 1982, summer of 2012. It's crazy. Earth's climate's changing. No, can't really dispute that. Difference between weather and climate, I'm sure you know that already. Things that can alter the climate over history: volcanic emissions, changes in solar input, movement of the continents, meteor impacts, changes in global air and ocean circulation. More recently, glacial and interglacial periods cause a lot of the climate change. So, obviously climate change is not a new thing, but it is being accelerated by human activity. You can see what's going on. So this is an image of excuse me. This is an image of climate change over 1,000 years. And you can see it kind of fluctuates pretty rapidly. This is us now. Yeah. Here's one of more recent, 1880 to now. This quick thing. The book that this PowerPoint's based on is like the 18th edition of Living in the Environment. I think Miss Cloudy's AP class uses like the 4th edition or something crazy like that. So this is from 2015, a bit more updated information. Figured it'd be a bit better. It's trended upwards since 1975. That's pretty obvious. This is how you take ice cores. You drill with this thing. And there's different sites you can drill at. This one is apparently near the South Pole of Antarctica. Why is it changing? You all know why it's changing. Burning stuff, global warming, blah. Greenhouse gases absorb the heat radiated by the Earth. You all know that. Cold and uninhabited without greenhouse gases. It can go either way. This is an awful picture. I'm not even sure what it's atmospheric lifetimes and warming potentials for the 3 main greenhouse gases. Not sure what that's even saying. Since the Industrial Revolution. Carbon dioxide. This is some kind of hydrocarbon, I'm not sure. And this is nitrogen oxide. No. Dinitrogen oxide. I don't know. They've been higher coming from agriculture, deforestation, and burning of fossil fuels. There is a correlation between rising CO2 and stage 4 with rising global temperatures. Bam. Look at that. This is atmospheric levels of carbon dioxide, and this is a global average temperature. Obviously, you can see there's a connection here. Use your average mean temperature, and then your CO2. Excuse me. Okay, here's what I'm going to do. I'm going to skip this one. Skip. Wait. Yeah, skip. Skip. So, we pretty much all know what's going to happen because of global warming. Temperatures are going to rise rapidly. These effects are going to be actually unevenly distributed. If you look at, more developing, poor areas, they somehow actually end up getting hit harder by a lot of this because they don't have the infrastructure to kind of manage a lot of this, including like sea level rise and stuff like that. Ice melts. As more ice melts, it releases more carbon dioxide, melting more ice, positive feedback loop. And then there's like the tipping point, basically. Once all this Arctic sea ice melts, it's pretty much all over at that point. Mountain glaciers are shrinking. They're important in the water cycle. Permafrost can melt. That's going to release a bunch of methane, which is a greenhouse gas, which is also going to accelerate. The Arctic sea floor even has methane in it. This is a projected thaw of permafrost in the Arctic tundra of eastern Russia. This is going to be between, this is the current, this is what it looks like now, and this is the next picture I'm going to show you. This is a projected amount between excuse me, good lord, between 2004 and 2100. That's a weird number. Tall shrubs and trees are going to take over what used to be Arctic tundra. Sea levels are rising. This is not good. We all know that. We all know that. This is what the U.S. is going to look like minus the red stuff. None of this is going to be here if it rises 1 meter. I mean, you've got a massive amount of Florida that's going to be pretty messed up. I mean, look, all of Miami is pretty much underwater. Oceans are becoming more acidic. Severe drought. Biodiversity. Amazon rainforest, 85% could be lost due to warming. Southern Ocean. Again, I'm going to post this PowerPoint on here. So as long as I've got like a 26-minute long video, it should pass from as cloudy's grade. Regions of farming are going to have less productivity in the northern latitudes. Not going to be as fertile. So this is going to, obviously we're already struggling with a growing population and feeding them and whatever, but millions of people could begin to face, millions of more people could begin to face starvation, malnutrition just due to climate change. Warmer world likely favorite things to make us sick. Bacteria like warm stuff. Most bacteria like warm stuff. Yeah. So this is excuse me. Good God. So all the blue stuff are counties. These are in 28 different states that, and this is where one or both species of mosquitoes that transmit the dengue fever have been found as of 2005. Basically, the entire southeastern United States has got this serious mosquito problem that could occur, especially with warmer weather. What can we do? We all know what we can do. Dealing with it, it's a global problem. Political issues need to be, sorted out before anything can really get done. I mean, humans automatically. Gosh, automatically, we're not going to really worry about the long term. I mean, most of us are going to be dead by the time we really start seeing some consequences to this. So we're like, well, whatever, right? But, long term, we should take care of the Earth. So you got the slow climb, right? And then as soon as you reach the tipping point, and it goes downhill from there. And then it kind of flatlines. It's like, the bottom of the pit. What are our options? I'm not sure why that's all grayed out, but you can see CO2, 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 carbon. Cleaning up greenhouse emissions. Apparently you can plant a bunch of trees. You can restore wetlands that have been drained. And use them as farming again. Plants take out greenhouse gases, basically. So the more plants you got, the less greenhouse gases you can, or the more oxygen you can produce by using greenhouse gases. Apparently this is some stuff we may see in the future, trying to so that's interesting. So these are geoengineering schemes, ways that we can reflect sunlight. This is like carbon sequestration approaches. This is all geoengineering. Just something to think about. Which of these do you think is probably the most workable? think about 3 of them, maybe. Greenhouse gases can be regulated as pollutants. EPA has classified several of these gases to be dangerous to public health. Fossil fuel companies obviously don't want regulation on them, so they're completely against this bill. You can put a price on carbon emissions, apparently. There's some stuff about using carbon and energy taxes to help reduce your gas emissions. Yeah. Here's that. Should have shut my door. Government subsidies can be used to address climate disruption. Subsidies can encourage energy efficient technologies. Phasing out subsidies on fossil fuels could, reduce the amount of people that want to use them. The government could fund research and development to switch to clean energy. Here's another thing you should probably know: the Kyoto Protocol, 1997, treaty to slow climate change. The U.S. did not sign this. It wanted to kind of transfer some of the knowledge that the more developed countries had to the poor countries to help them kind of get a start without being so energy, without using so much fossil fuels. Costa Rica is supposed to be carbon neutral by 2030. I think they've actually already achieved this. I think the thing is that Costa Rica actually gets a lot of their energy from other places, like nearby islands or whatever. I think there's something with that. U.S. cities and states are actually taking some initiatives to help reduce the carbon emissions. Examples, pretty much the entire state of California and Portland, Oregon. Companies are also working to reduce their carbon footprints. You've got these companies, Walmart, Apple is actually net positive. They produce more energy than they use from all their solar stuff. Thinking about every text you send, that data centers fueled by renewable energy. Their manufacturing in Asia is still not, but they're working on that. Colleges and universities are going green. Arizona State has solar panels. College of the Atlantic has apparently been carbon neutral since 2007. University in Costa Rica. Carbon generated either directly or indirectly by a person or group, and things like your diet and your non-food purchases can all be combined into your carbon footprint. And using this carbon footprint can actually help you determine what you can kind of do to help reduce the amount of carbon you emit. There's some stuff that you can do. Think about some steps you might be able to take. How can you adapt to climate change? Realizing that there's a lot of these benefits by reducing the greenhouse gas emissions are pretty much the only way we can avoid this. How can we reduce greenhouse gases again? Move people from the low-lying coastal areas into new areas so they're not going to be frantically displaced and stuff. Take measures against storm surges, prepare for more intense storms and wildfires, and conserve our fresh water. Here's a diagram for some ways that you can prepare for the long-term harmful effects. No regrets strategy. What if climate models are wrong and there's no serious threat of climate change? Any actions against climate disruption are going to lead to important benefits anyways. So, 3 big ideas, apparently. There's 3 of them. So, this is the end of the PowerPoint. I honestly hope you learned something from that, because I just sat here for 35 minutes and was talking to myself in my room. Hopefully you didn't get bored and die. If I yawned and you yawned too, because the yawns are contagious. Hashtag yawns are contagious. Just give me a thumbs up, whatever. You know, I don't know how to get out of this. I don't know how to get out of this. Crap. Oh, yes, I do. I do know. Okay. Adios, y'all.